A linear regression model assumes that the regression function is linear in the inputs. So this is the regression function, and we can see here that the inputs beta here are linear, right? There's no beta squared or square root beta or anything like that. Now, earlier we showed that the best possible predictor under squared error loss is the conditional expectation here, the regression function. Now, chapter 3's entire premise is what if we just assume that this function here is linear? And to be clear, this chapter is about regression, meaning quantitative y, and the classification where y is categorical gets its own treatment in chapter 4. So here's our model. So our model, of course, is just a function which takes our inputs and it applies some linear weights to our inputs. But the weights being linear is what's important. So this xj, it could be xj squared or square root xj, that's fine. It'll still be linear in the betas. All right, so exactly like week 22, we need a loss function. So we're going to use the residual sum of squares. Okay, so the residual sum of squares is just the sum of the squared residuals, as in the name here. And so plugging in our model here for f, we have the following expression. Now we can write this in matrix notation as follows. We can expand this out as follows. And notice that these terms here are actually scalars, right? They're scalars, so we can therefore combine them and also take the transpose. So we get the following expression here. Now, of course, we want to minimize the residual sum of squares, and so we have to take the derivative with respect to beta and set that equal to 0. So just taking the gradient here, it gives us this expression, and then we can simplify this more by factoring out the negative 2 x transpose. And then when we set this equal to 0, this constant goes away, and you might be familiar with this expression. Great, and then solving for the beta here, we get the normal equations, which minimizes the residual sum of squares. Now, once we have these betas, we can plug these guys back into our function. So our function can be written as x times beta. And so therefore y hat is equal to x times beta hat. And so simply plugging in this beta hat here, we get this equation. And notice that we can denote this this sort of term here as the H matrix. We call it the hat matrix because applying the hat matrix to y kind of applies the hat symbol to y. So it turns y into y hat. So to summarize what we did, we first defined some model, right? F of x is equal to x times beta. And our prediction is f hats, which you can say is y hats, is equal to x times beta hats, where beta hat is the parameters which minimizes the residual sum of squares. Or it can actually be any loss function, but we're just looking at the residual sum of squares. So then we found the beta, which minimizes the residual sum of squares, and of course that's beta hat. And so that gave us this expression after setting the gradient equal to 0 here. And then we solved for beta, which gave us this expression here. And then finally, we plug that back into this equation right here and define this hat matrix, which puts the hat on y. Now, the book kind of gives us two different ways to visualize it, and I think both of them are pretty clarifying when working together. So the first space is the one you probably draw naturally, which is called the feature space. So, if you only had one input and one output, you draw a 2D scatter plot, sort of x on one axis here and y on the other. And then you plot your n data points here, and you draw a line of best fit defined by your betas. So this diagram is a pretty natural way of visualizing the space. You're just plotting your features, and then you're plotting your response orthogonal to all of your features. And then what you want to do is you want to minimize the vertical distance, right? This is yi minus your prediction, right here. So it's your prediction, and this is your actual yi, and you want to minimize the distance, or in this case, the square distance, right, across all points. So that's pretty intuitive. But there's a second space, and this one's less intuitive at first. This is called the observational space. So instead of a one axis per feature, imagine one axis per data point. If you have n observations, the observational space is in R of n. Your entire target vector y, every single yi here, is now just one point, or really one arrow in this n-dimensional space. In other words, each column of your X matrix, so let's call it the jth column or xj, is just a vector in that R of n space. So here's a example just to illustrate that some more. So let's say that n equals 300. So you have 300 data points, and p equals 2. So this is your number of features. That means your observational space is in R of 300. That's pretty big. But a linear regression model can only ever produce predictions that are linear combinations of the columns of X, right? That comes from linear algebra. So with only two features, plus the intercept column, of course, that's three columns. So every possible prediction y hat must lie within this R of 3 space. So ESL calls this space the possible values that your model could predict the column space of X. So you can think of it as sort of a flat sheet going through this super high dimensional space here. All right, so on the left here is just abstractly representing what I mean. So this entire space here is R of, in our example, 300. So this is R of n. And then this column space of X, this plane here, is the possible predictions that our model, could predict. And this is where y hat lives, right? Y hat. Now, of course, in reality, because this is R of 300, the true predictions, lies elsewhere. It lies outside, most likely, of this column space of X. In other words, if you go back to the other picture, these points do not lie perfectly on the plane. In fact, we cannot find a line which perfectly has all the y values on this plane. This is the same idea, just in different view. So the best our model can do is find a single point on this plane which is closest to the actual value of y. And so how do we find that point? All we have to do is project the actual value onto the column space perpendicularly. If it wasn't perpendicular, then this would not be closest to the value of y. In other words, the residual vector, so y minus y hat, must be perpendicular to the column space of X, which of course means that X transpose times y minus y hat is equal to 0, and y hat is equal to X times beta hat equals 0. Now, wait a second, this is exactly the equation we saw earlier from doing our calculus and minimizing the residual sum of squares. And so from the geometry, it directly falls out the normal equations, and that gives us the hat matrix. You can think of the hat matrix as a projection matrix onto this column space of X. So just going on a tangent here, this is one of my favorite things about regression. It's simultaneously a calculus problem we saw earlier, as well as a projection problem from linear algebra, right? And also a convex optimization problem from the Boyd sense, which we minimize. There's an optimization problem underneath this. So the whole first half of the series was exactly about the shape of this problem. Lastly, what if two columns are collinear, meaning one feature is a linear combination of the other? So for example, if 3xj is equal to xj plus 1, then there's no extra information contained in xj because that's already contained in xj plus 1. What that means geometrically is that this column space is not full rank, right? If p equals 2, so because there is the intercept, there's 3 dimensions here. If one column is a linear combination of the other, then this column space is no longer 3-dimensional. Maybe it's 2-dimensional. However, that does not prevent you from still projecting your solution down onto your column space. All that does is it prevents you from having a unique solution. You no longer have a unique solution. So now there's infinitely many betas which can land on this space. So this is because this column space has sort of, quote unquote, lost a dimension.